forced-derived 86 olivine. And if we add some forced-derived 86 olivine into it to correct for fractionation, it will evolve this way until it's at this composition in equilibrium with forced-derived 87 olivine, and so on back along this olivine control line, which is a curve, not a line, until you get back to equilibrium with mantle olivine way up here at 15% MgO in the liquid and a liquidus temperature of 1350 degrees. Okay. However, if you started with your analyzed glass and you said, oh, wait a minute, that measurement of total iron is not all FeO, some of it's Fe2O3, then you're going to start from a point somewhere down here. And here's three different places you might start from. You might start from the Christie et al. Number, you might start from the Bezos and Humler number, you might start from the Cottrell and Kelly number. It's very unlikely that you've actually measured ferric iron or ferrous iron or total iron in this glass, because that's a really hard measurement. So you're probably taking your major element analysis of this glass, and you're assuming the oxidation state of typical mid-ocean ridge basalts based on one of these studies. Right? And so if you lower the FeO content, you come into equilibrium with more magnesium-rich olivines at the collected composition. And you don't have to correct as far back to get back to equilibrium with mantle olivine. And you end up with lower MgO in your primary liquid at a lower liquidus temperature. And in this simple model, this is the range. Okay? For the range from Cottrell and Kelly magnesium or oxidation state to Christie et al. Oxidation state, you go from about 10% olivine addition to about 13% olivine addition, and you change your estimate of the liquidus temperature by about 30 degrees. Okay? This is not far from the way it actually works, and it's pretty straightforward to visualize. So is everybody with me so far, right? If I come along and I have an electron probe analysis of the mid-ocean ridge basalt glass, but I have to infer from a different source how much of the iron is ferrous, that affects what I think the olivine, that is the last olivine crystallized from that liquid would be, and it affects how much magnesium oxide I would think I need in order to correct back to mantle compositions and what temperature that would have. Now, let's do that a little better, a little more carefully. Okay? I made some assumptions in drawing that previous diagram. I assumed that the KD is always exactly 0.3, and I assumed that mantle residues always have forced-derived 91 olivine, neither of which is true. Okay? So there is a model out there that I have helped to release and distribute and develop to some extent called Primelt3. It's the current generation of a model that was proposed by Hertzberg and O'Hara in 2002. And the basis of this model is if you have a glass or a hull rock which is only olivine saturated, so it has to be fairly primitive to begin with, and you cannot find such liquids in all of the world's basalt terrains, but if you have one, and you can incrementally add olivine back into it, it's going to follow a control line that goes like this up towards high MgO. And if you compare that in FeO MgO space to melts of mantle peridotite, okay, you can contour this space for the extent of melting. Okay? The solidus, 0% melting, is just a straight line because your source peridotite has a certain magnesium number in its olivine, and that corresponds to a certain magnesium number in the liquid. But as you melt peridotites, they move in this direction, okay, and the liquids become higher in MgO and equal iron. So for each of these points that is a possible parental liquid to this collected liquid, you can read off from this diagram an extent of melting. Now you can also plot those candidate liquids in this space, which is a projection of the normative mineral space, olivine, quartz, dioxide, anorthite, where you can also contour the results of peridotite melting experiments for extent of melting. The solidus of peridotite projects here, the 10% melting contour projects here, in the spinel lexolite field and garnet lexolite field, and so on. And so from your collected rock back up your liquid line of descent that is derived by adding olivine into the composition, so it goes that way, you can read off an extent of melting for each of those points. And there is one, and only one, point along that liquid line of descent that gives you the same extent of melting both in this diagram and in this diagram. And the Primelt model says, okay, that's a candidate solution of taking a peridotite, melting it to a certain extent, making a liquid, and fractionating it that consistently explains your observed glass composition. Okay? And the model includes a better formulation for KD than it's just 0.3. And it does not assume that the residual olivine has a certain composition, because the hotter the region is, actually, the more magnesium the residual olivine will be. So it's a better formulation. Okay? But it's conceptually similar to that simple diagram I showed you. And this is an example of the results. Okay? This is a particular mid-ocean ridge basalt glass, in this case from the Pacific. Okay? The collected glass has 9.84% MgO. Okay? And if I vary in the model my estimate of ferrous iron over total iron, okay, and I've here shown a full range from 0.8 to 0.96. Okay, and the plausible range that's been proposed, right, is from 0.84, Cuttle and Kelly, to 0.88, Bezos and Humler, to 0.93, which is actually here, which is Christie et al. Okay? And what the model says is, in order to get a successful solution for a primary liquid with these values of ferrous iron over total iron, okay, you need to add somewhere between 0 and 9% olivine to go back up to the liquid as fractionated rock. You will end up with somewhere between 9.84 and 13% MgO in that primary liquid. Okay? And that primary liquid will be derived from somewhere between 5% and 12.5% average melting of the mantle, which is quite a wide range, because that's more than a factor of 2 in your estimate of the crustal thickness that you're going to get by melting the mantle. Okay? And so across this range, it varies from about 7% to about 11% mean extent of melting. Same calculation in terms of temperature, as we go from 0.84 ferrous iron over total to 0.92. The estimate of the liquidus temperature goes up not 30 degrees, but 40 degrees in this more complicated model. And our inference of the potential temperature of the mantle goes from 1320 up to 1365, a range of 45 or 46 degrees. And remember that in all of the models of mantle melting, a change of the potential temperature of 25 degrees changes the crustal thickness by a kilometer. So this range changes your estimate of how thick the oceanic crust should be by about 2 kilometers, which is a lot, I think. Okay? So what happens if you change your estimate of the potential temperature by 46 degrees, simply because you changed your estimate of the redox rate? Okay, well, you can't really answer that question using PriMelt3, because what I've shown you that PriMelt3 does, that's all that it does. Okay? It doesn't describe the whole geometry of the melting regime under a mid-ocean ridge, and it doesn't describe the fractionation of pelagic place and pyroxene, only olivine. So it can't actually get you all the way down to the composition of the basalts that are erupted on most ridges. Okay? Instead, I'm going to turn to the other model that I am involved with, the PMELTS model, which is a more detailed thermodynamic formulation that you can apply to all of the parts of the mid-ocean ridge melting and crystallization problem in a consistent way. And it will allow us to follow up on the implications of changing the potential temperature. Okay. So, as I said, PMELTS is a thermodynamic model that predicts crystal liquid equilibria in a self-consistent way. It can describe both granite-type melting and basalt fractionation. It conserves both mass and energy, which most petrological models do not. And therefore, it allows us to say, as we take a parcel of mantle and decompress it, what the pressure temperature path will be and how much melt will be generated in an energetically consistent way. And this model does a really remarkably good job of describing the mantle melting problem. Just as an example of how well it does, the dots on these diagrams are every glass analysis from these specific rise that's in the petrological database of the ocean floor. And the curves show primary melts derived from passive flow type mid-ocean ridge melting regimes at 3 different potential temperatures ranging from 1329 to 1377. And then these lines are their isobaric fractional crystallization paths during differentiation in the crust. And you can see that basically you can map out every glass that you can find on these specific rise with a range of about 50 degrees in potential temperature and a range of extensive fractionation that takes you from about 9% to about 6% MgO. Makes explains the silica, it explains the total iron, it explains the calcium, it explains the titanium. It sort of explains the aluminum, although there's something funny with the slope, and it sort of explains the sodium, at least the average value. Okay. So I like this model because when I go and I pick up a glass from a mid-ocean ridge, I can turn around and I can say, this glass fractionated from a primary rock up here with this temperature that came from a mantle with this potential temperature. And I can turn around and say, if that's the potential temperature, then the crustal thickness should be a number, and I go back to that place where I collected the glass and it matches. So here's what happens in the MELTS model as you change the potential temperature by 46 degrees from 1365 down to 1320. Okay. The magnesium oxide of the primary liquid goes down by about 2 to 8%. And as we predicted, the crustal thickness goes down by about 2 kilometers, from 7 kilometers to 5. And 7 kilometers is a good number for the thickness of the oceanic crust, and 5 is not. How not is it? Well, here is a somewhat old now compilation by Bob White of estimates of oceanic crustal thickness at lots of places on the mid-ocean ridge, either by seismology, where you directly image the MOHO, or by inversion of rare earth elements, which is a Cambridge model-dependent way of doing it, but they've made them agree with each other, okay, versus the full spreading rate in millimeters per year. And for normally spreading up to super fast spreading ridges, this number is 7 plus or minus 1. It is clearly not 5 until you get down to ultra slow spreading ridges. Likewise here, it's 7 plus or minus 1. It is definitely not 5. And here's the sort of scary thing about this freedom to play around with the redox state. What you see here in sodium versus MgO and in total iron versus MgO are 4 models, all based on the P-MELTS model, where I have varied the iron 2 plus over total iron over the range that has been proposed, corresponding to these oxidation states, and I've adjusted the potential temperature until I found a solution which goes through this particular body of data for this particular segment of the Mid-Atlantic Ridge. Okay? And all 4 of these models yield basically the same liquid iron descent with the same sodium 8 and iron 8, which are the numbers that people use to express extent of melting and pressure of melting. Okay? And yet, one of them is consistent with 5 kilometers of crust, and one of them is consistent with 6.5 kilometers of crust. And at this location on the Mid-Atlantic Ridge, there's 6.5 kilometers of crust. Okay? And so the chemistry by itself, if you don't actually know how much of the iron is ferrous, cannot be used to uniquely invert for how hot the mantle is or how thick the crust should be. Now, we have some other constraints on the potential temperature of the mantle. For example, if you look at the S-wave velocity in, I think this is your Ritzman's model, at 300 kilometers depth, right under the ridge axes, and attempt to convert that S-wave velocity to a temperature, this is what you get. The range is from about 1320 to about 1470 right under Iceland, and the mean is 1360. The mean is definitely not 1320, although there are places that are as cold as that. They are isolated cold spots. Now, let me move on to the next issue, other than you cannot, if the mantle is cold enough to yield these cold primary liquids, which don't fractionate very far, you can't get enough crust. You also specifically can't get enough lower crust. Okay, so this is the seismic structure of typical oceanic crust, or typical spot of the ocean. Here's the P-wave velocity of seawater, here's the sediment layer, here's what's called layer 2, which is the extrusives, the pillow basalts and the sheeted dikes. Here's what's called layer 3, which is thought to be the intrusives, the gabbros. Then there's the MOHO, and you're into mantle. And you will note that the plutonic lower crust, layer 3, is always, everywhere that I know of, thicker than the upper crust. There's more cumulates than salts. Also, the velocity of the lower crust, which ranges from about 6.5 to 7 kilometers per second P-wave velocity, is consistent with mafic cumulates, with gabbros. It's not consistent with the salt. Also, when you go to ophiolites, where we have exposed sections,